So, early careers presentation. To kick us off is Maria Akiki, who is a PhD student at IMT. She's in the second year of her PhD with a study named Detection of VOC Biomarkers in Breath for Chronic Kidney Disease and has been using the Receiver device for this. She previously studied in Lebanon, studied analytical chemistry, and work included analysis, migration of plastic additives in bottled water by HPLC. So over to you, Maria, and thanks for joining us.
Hello everyone, my name is Maria Aie. I'm a PhD student in third year at IMT Lille, France. Before I begin my presentation, I would like to thank you for giving me this opportunity to participate in this conference. In this speech, I will present the results obtained during my first 2 years of thesis, detection of VOC biomarkers specific to chronic kidney disease by analysis of exhalate air from dialysis patients at advanced stage. This work is directed by Nadine Locage and François Glovaski and supervised by Jean-Luc Voschkevich and Caroline Duc. It's funded by University of Lille, Terra Environnement and European Union, and it's in collaboration with CHU of Lille. First, I will start by a short introduction of chronic kidney disease. Then, I will present the materials and methods used for this work, Receiver breath sampler, Alston, and the analytical system TDGC FEDMS. A breath sampling, it's done for 43 chronic kidney disease patients at CHU of Lille, nephrology service, and an analysis is done after to study the variation in the concentrations of VOC detected during dialysis. Kidneys are vital organ in the body and perform several functions like elimination of toxic waste like urea and balance of minerals necessary for the body. Nephron is the functional unit of kidney. It allows to filtrate blood. After filtrations, there are reabsorption of the solute and water in blood, and the toxic waste were excreted by urine. Chronic kidney disease is characterized by a progressive and irreversible decrease in renal function. And when the patient arrives to a terminal phase, chronic renal failure, a treatment of dialysis is necessary to do, and then a kidney transplantation. To detect this pathology, patients need to do a urine test to measure urea or a blood test to measure creatinine. After these two tests, a treatment of hemodialysis is necessary to do to the patient. There are exchange between the blood and dialysate outside the body using a membran. The objective is to eliminate toxic waste and equilibrate the blood composition. In France, for example, there are more than 87,000 patients treated for chronic kidney disease at advanced stage, and this treatment costs 4.18 billion euro a year. Because these two biological tests are done at advanced stage of the pathology, and because the cost of the treatment of dialysis is high and the number of patients increase year after year, so a new approach is under study recently, and it's based on a breath test to detect VOC biomarkers specific to chronic kidney disease at early stage. The problematic of this work is it possible to establish a VOC fingerprint typical of chronic kidney disease? So, what is the sampling and analyzing methodology we have used to collect the breath samples of patients in this work? This is the way how the sampling goes. First, we collect the breath of patients doing dialysis with the sampling device receiver. 4 tubes were inserted into the mask of receiver to collect the breath before and after dialysis. With this sampling device, there are many parameters to optimize. So a procedure of optimizations is done before to start the collection of patient's breath. Alveolar air is collected with a flow of 50 milliliters per minute with a volume of 500 milliliters. After the step of sampling, the tube were thermally desorbed and then concentrated in a trap to be after injected in the column of GC. The VOC were identified by MS and quantified by FED. Also, with this analytical system, a procedure of optimization is done to be able to detect a large number of VOC with different chemical family. There are the parameters optimized for the first thermal desorption and also for the trap. After the procedure of optimizations, a breath sampling is done at CHU of Lille for 43 chronic kidney disease patients with different gender and age. For each patient, alveolar air was collected on 4 tubes before and 4 tubes after dialysis. After, all the tubes corresponding for the 43 patients were analyzed, and the results of the concentration of the VOC detected were collected in a huge table. Here we have a part of this table containing initially 43 columns corresponding for the 43 patients with 356 lines corresponding to the 356 VOC detected with their concentrations microgram meter cube. Later, a strategy is done to analyze these concentrations of the VOC detected. The identifications and quantifications it's done for 356 VOC. Then a selection is done for this VOC. Each one is found in less than half of the patients tested. It's not analyzed. We analyze just the VOC found in the majority of the patients. Then the VOC selected were grouping according to their chemical family. And a box plot is done for each VOC to compare the concentrations before and after dialysis. A statistical test, Wilcoxon, is done to calculate p-value for each VOC. Then this p-value is compared to alpha. If p-value is less than alpha, the significant threshold, so the difference between the concentrations before and after dialysis is significant. And if p-value is below than alpha, so the difference is not significant. Now, in this slide, I will show you the result for the chemical family alkane. In general, we detect 46 VOC alkane in breath of the 43 patients tested. Out of 46 VOC detected, only 20 have been found in all patients and will be analyzed after in this study. In this table, I'm showing you 3 VOC, for example, out of 20, classified according to their frequent appearance in the 43 patients. The third columns present the significant impact of each VOC during dialysis, and then we have the statistical values before and after dialysis. The last columns present the box plot and p-value for each VOC. For example, for pentane, there are 2 box plots which summarize the distribution of the statistical values before and after dialysis. Box plot is between the first and third quarter. Medians decrease after dialysis, and the interquarter range is double before compared to after dialysis. Also, the distance between the 2 mustache is double before compared to after dialysis. So, this decrease in concentrations after dialysis is significant and conformed with a p-value less than alpha. Here, a summary for the 20 alkanes found in breath of the 43 patients tested in this study. 10 alkanes present a decrease in their concentrations after dialysis, and this decrease is significant and conformed with a p-value for each VOC less than alpha. And the 10 other alkanes present a non-difference significant in their concentrations, and this is confirmed with a p-value below than alpha. So here we have the 26 VOC with different chemical family that present a significant variations in their concentrations during dialysis. As we can see, 24 VOC decrease in their concentrations after dialysis. 10 alkane, 1 aromatic, 1 furan, 9 alkene, 1 aldehyde, and 2 alcohol. At the same time, 2 VOC chloride increase in their concentrations at the end of dialysis. All these variations is confirmed as significant with the statistical test. The VOC in red were identified by MS and confirmed with an individual standard injection, and the VOC in black were identified by MS and the confirmation with the standard injection is in progress. So now we will compare these results obtained in this study with the bibliography. In the bibliography, we found 3 references that detect VOC in breath of chronic kidney disease patient. Joel and Mochalski detect VOC and compare their concentration during dialysis, but Grabowska's study detects VOC before dialysis and then compare with a healthy population. Some of the VOC found in these 3 references were comparable to the VOC detected in our study. So, this table shows us the comparison of the VOC and their values in the 3 references with our study. When we compare the median concentrations, we see that the value found for butane, for example, before dialysis in this study is comparable to the value found in Mochalski's study but after dialysis. So, at the level of quantification, we are not comparable, but we present the same negative variation of concentration. Same cases for pentane, the values of median concentration before dialysis are so far. It's between 0.1 and 10 ppb. But in the 3 studies, the concentration decreased after dialysis to reach values between 1 and 2 ppb. Also, for eptane, 2-methylpentane, and toluene, the variation of the concentration is negative in this work like Mochalski's study, but with different values. So, to conclude, we found in the bibliography 7 references which present an objective to detect VOC biomarkers in breath of chronic kidney disease patients and compare the VOC during dialysis or with healthy population. These studies present different results with different VOC detected. This variability of detection is due to different parameters like number of patients, sampling methods, or analytical system. In this work, 26 VOC were detected. There are some of them like butane, pentane that were identified before in other reference. But we have also some VOC detected that it's not appear before in the bibliography and it's interested to verify and confirm it after. Finally, it's important to focus our perspective on the 26 VOC detected as sensible in chronic kidney disease population, but especially on the VOC that we didn't find before in bibliography. At the end, a comparison with the VOC detected with a significant variations during dialysis in patients at advanced stage is interested to do with the 2 other populations. Patients with chronic kidney disease at early stage and with a healthy populations. And another study it's important to test it's the correlation of the concentration of VOC with a significant variations during dialysis with biological data like urea and creatinine concentrations. Thank you for your attention and hope this presentation interested you.
Thank you so much. That was fantastic. If you could start your camera and microphone, we have time for a couple of questions.
Hello, Billy. Hello, everyone.
How are you doing? So I was hoping to kick us off. So I think you said that you confirmed the ID using pure standards for some of those compounds.
Yes.
I was interested to kind of get a bit of a sense of if you have a view of what the biological origin is of some of those compounds, their significance, and also what the kind of plan is from here. Is there subsequent studies being planned where you do have these confirmed IDs and looking into the additional samples?
Yes, in fact, we detect this 26 VOC with a significant variation. So at the level of the detection and the variation, we are confirmed. But now the perspective, it will be to compare this VOC with a population at early stage to see if we will detect it and to compare the concentration. So if we will find that the concentration of this VOC, it's comparable to the concentration found after dialysis, it will be the objective of the study, and also we will see if there are correlation between the biological data. So if there are the confirmation of the importance of this VOC, it will be done.
Brilliant. What do you think? There's one here. Do you expect most VOCs to go down as a result of dialysis? Was it mostly the larger molecules, and do you find these compounds in the dialyzed fluid?
Yes, in fact, we have 2 VOC chloride that increase in concentration. So I think their origin it will be from the membrane or tube of dialysis. So now we collect the data of the tube that we use in the SHU to compare their composition and to see if there are chloride. So it will be interested to see.
I think that Terence raised a point yesterday that studies where people are acting as their own control tend to be quite powerful here. So I think those results look really nice. And I think you were talking about how some of the absolute concentrations are maybe a little different between different reported literature, but directionally they're all the same. So you have that decrease
Yes.
in intensity. So do you think it's just the differences in the analytical techniques or the calibration maybe that accounts for those differences?
I didn't hear the question, please.
For the differences in the concentration, so
Yes.
between the different what was reported previously in literature. So do you think that's just different analytical techniques that were used? Or?
Yes, in fact, we have a difference in the quantification. It will be due to different reasons. The first, the number of the patient tested. We are different. The second, the sampling methods. Sampling on tube or tabular bags or collection bags, and the analytical methods. We have sometimes online methods like PTR, and the majority of the time you have GCMS. But in the GCMS, you have different parameters adapted for the thermal desorption or the trap. So in fact, this variability in the parameters can explain this variability in the concentration.
Thanks again, Maria, for that work. Really interesting. Much appreciated.